Hello, math humans. I have to confess, I told you a story yesterday. I said 3.4b was our last video. Just kidding. So today we're going to do 3.5. We're going to talk about exponential and logarithmic modeling. So our objectives are that we're going to talk about the three common models for exponential and logarithmic modeling. Exponential growth and decay, the logistic growth or decay model, and then the logarithmic models. So let's start off with the exponential growth and decay. So there's two basic different forms of this equation. In previous math classes, you might have seen it as y is equal to a b to the x. And in my opinion, this one is great if you're doing half-life problems. Okay? And then the one that your book introduces is y is equal to a e to the bx. It is growth if b is positive, and it is decay if b is negative. So let's kind of compare each one. You can use this one for half-life problems. You can use either for half-life. I just think this one is easier. A is going to be the initial amount. B is going to be the rate of change. So if it is growth or decay, that's what B represents. If B is greater than 1, it's going to be growth. And if B is less than 1, it's going to be decay. And if you are doing a half-life problem, the equation is going to be y is equal to whatever your initial amount is times a half, because whatever thing is halving every so often, and then it's going to be raised to the x divided by the half-life period. So even in calculus, if my students have to do half-life problems, I tell them to use this formula because I think it's easier. This one is an expectation, though, so we need to learn how to use it. A is still going to be the initial amount. B is still going to be the rate of change. And then in this one, if B is positive, then it is growth. And if B is negative, then it is decay. Okay? Both models basically look like an exponential function because that's what it is, and it crosses there. All right, so that's the model for growth because the value is increasing, and then decay would be basically the same graph, crosses at 1, and there we go. So this would be our decay graph. All right, the next function that we want to talk about is the logistic growth, and it's actually a really cool function because it's one of the only functions to have these special characteristics. So in the logistic growth function, here's my x and y axis, it is one of the only graphs that has two horizontal asymptotes. Okay, so it has two horizontal asymptotes, and then my graph is going to look something like this. The top asymptote is called the carrying capacity, and again, it depends on what book you're using. It's also called the limit to growth, which means that this is the absolute capacity that something can be. This is often used in science because maybe a population of animals can only be supported by water, food sources, and other things, and so there is a limit to how many animals can actually grow in that particular area. So the formula is y is equal to a over 1 plus be to the negative rx. A is going to be the carrying capacity, we've already written this down, or the limit to growth. And it is one of the only things that if a question is asked, what is the limit to growth, then I just read that from the numerator. Okay? B is I'm not going to define it. I was going to define it as an initial amount, but sometimes that is misleading in this equation. So I would say that the initial amount is better calculated when x is equal to 0, and then you can find your initial amount by substituting in the other values that you know. R is equal to the rate of change, and then x is always going to equal time. So we're going to go now and walk through two different examples. It would help if I turned all my lights on so you guys could actually see. Oh, look at that. So we're going to do an example of each of these two methods. So let's just go ahead and start. And look at that. Magic happens, and the example has already been written. To save us some time, I pre-wrote them out. In a research experiment, a population of fruit flies is increasing according to the laws of exponential growth. After 2 days, there are 100 flies. That's gross. And after 4 days, there are 300 flies. That's even more gross. How many flies will there be after 5 days? So this is actually a really interesting problem because what happens with the situation that's set up before us. So I'm going to write down what I know. I know that after 2 days, I have 100 flies. So this is my days, and these are my flies. And then I have 4 days and 300 flies, okay? And we know that this is exponential growth, so I'm going to use the model AE to the BX. The problem in this particular problem, it's a very classic problem, is that I have two variables. I don't know A and I don't know B because it doesn't tell us what happens on the initial day, and it also doesn't tell me what the rate of growth is. But I know an X and a Y and an X and a Y. If I have two variables, then I can write two equations. So here's what I'm going to do. I'm going to fill in what I know, and I'm going to write two separate equations. So from the first data point, I'm going to get 100 is equal to AE. The time is 2, and then I have a B. And then I'm going to do the same thing. I'm just going to do it over here a little bit. 300 is equal to AE to the 4B. In this particular situation, I'm going to solve both equations for A. So A is equal to 100 over e to the 2b, and in this one, A is equal to 300 over e to the 4b. In the same problem, the A's are equal, so I'm going to set these two things equal. So I get 100 over e to the 2b is equal to 300 over e to the 4b. Then I am going to cross multiply. So I'm going to get 100 e to the 4b is equal to 300 e to the 2b. I need like things to play together, so I'm going to do some division. Okay, and I'll scoot my paper over a little bit. So I'm going to have e to the 4b divided by e to the 2b is equal to 300 divided by 100, and I'm going to write a 3. Okay, now I can reduce this. 4 minus 2 is 2, so I get e to the 2b is equal to 3. Well, because I know how to do math with logs, I can solve, so I can take the log of both sides. So I'm going to get 2b natural log e is the natural log of 3. The natural log of e is 1. So b is going to equal the natural log of 3 divided by 2. And at this point, I'm just going to leave it like that because my answer will be more precise if I don't get a decimal equivalent, and I'm going to put a box around it so I can find that later. Well, I now can find a value for A, so I'm going to use the first one just because it's the first one. E to the 2 times the natural log of 3 divided by 2. The 2's cancel, so this is 100 over e to the natural log of 3. Okay, and that would be my A. So now I'm going to write my model. So my model, which was y is equal to AE to the BX, y is going to equal A, and it's okay if you leave it like this. So I'm just going to write 100 over e natural log 3. Here's my e, raised to the b, which is the natural log of 3 over 2, times x. Okay, so there's my model. The question said, how many flies are there going to be after 5 days? So the reason that I didn't get the decimal equivalence, because when I substitute in the 5, which you can't see, now you're going to get a better answer. So f of 5 is going to equal 100 divided by e natural log 3, and then I have an e natural log 3 divided by 2 times 5. And when you do that math carefully in your grapher, you're going to get 519.615 flies, but 0.615 of a fly is gross. So I'm going to round up and say that f of 5 is equal to 520 flies. That's a lot of flies. So it's actually really pretty easy. But let's go back and talk back through what we did. This is just data from the problem. I recorded it so that I know I have x's and y's. This is the model that I'm going to use. I wrote 2 equations. I solved both of the equations for a. The a's are equal, so I set the two a's equal. I solved for b. Then I could go back and solve for a. I can write my model. It's always important that you write a model that you can't see. There it is. And then this particular problem, all it asked me to do was to predict. Now on a test, you always have to record the model that you find. And I would have been okay if you had gotten some decimal equivalents, but remember your answer will be more accurate if you don't. And then this particular problem asked me to predict. This shows that I evaluated the model at 5, and then I found my particular answer. All right, so that was our first example. Now we're going to do the second one, which is also miraculously written down. Look at that. This one I think is entertaining because our book is older than dirt. And this example, I've been teaching this example for years. It just seems to be extra relevant right now. On a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting virus. The spread of the virus is modeled by this particular equation, math, and notice that it's a logistic growth model. Y is the total number of students infected after T days. The college will cancel classes when 40% or more of the students are infected. And then it says how many students are infected after 5 days, and then after how many days will the college cancel classes. So it's just as fascinating to me that we are doing this math right now. All right, so the first question says how many students are infected after 5 days. So I'm just going to write my model down here just because it's handy. So I have 1 plus 4,999 e to the negative 0.8t. So all I'm going to do is do f of 5, and I'm going to substitute the 5 into this equation. I'm going to do all of it in my grapher, and I'm going to get 54.019, and it says how many students. Because I'm talking about humans, 0.019 of a human is gross. So I'm going to say that after 5 days, there are 54 humans that are infected. Okay? So in 5 days, we went from 1 to 54. So the second part says, how many days will the college cancel classes? Well, there are 5,000 students, and it said it will cancel classes when 40% of them are sick, and so that's 2,000. So then what I'm going to do is I'm going to set the 2,000 equal to the 5,000 over the 1 plus 4,999e to the negative 0.8t, and the goal is to solve for t. So the first thing that I'm going to do is I'm going to cross multiply, but I am not going to distribute. So I'm going to get 1 plus 4,999e to the negative 0.8t times 2,000 is equal to 5,000. I'm going to isolate the t. 1 plus 4,999, that's a lot of negative 0.8t, is 5,000 divided by 2,000, 1, 2, 3, which is just 5 halves, okay? Subtract 1, so the 4,999 e to the negative 0.8t is 5 halves minus 1, okay, which is 2.5 minus 1 is 1.5. I'm still trying to isolate my t, so I'm going to divide. So e to the negative 0.8t is equal to 1.5. I'm not going to do this math because it's not going to be a pretty number. Now what I'm going to do is take the log of both sides. So I'm going to do a negative 0.8t. Natural log e is the natural log of 1.5 divided by that number. And again, I'm not going to push buttons on my grapher yet. The natural log of e is 1. Now I can actually solve for t, and it's going to be the natural log of 1.5 divided by that number divided by a negative 0.8. And when I do that math, I get 10.139 days. So after 10.139 days, the university will choose to cancel classes. Alrighty, that is it for today. I will see you soon.